My name is Charlie Hull from Open Source Connections, and I'm going to be introducing an old friend and colleague, Rene Kriegler. So Rene's been working in search for about 10 years now.
13.
13, it's not up to date, this. Often actually contracting for Open Source Connections. And he also worked with me in my UK business, Flax, before we merged with OSC. He's been working in search and LP, relevance consulting, and particularly on e-commerce. And he mainly works with Solar and Lucene. He organizes the MICE's e-commerce search conference, which is in Berlin this year, just after Berlin Buzzwords, which I'd highly recommend to you. And also maintains Quirky, which is a query rewriting library for Solar and Lucene. So he's also a very clever man, generally nice chap. And I will happily introduce him, and I'm sure generally. You will find his talk hugely interesting. So, ladies and gentlemen, Rene.
Okay, thank you. Yeah, thank you very much. Yeah, I think Charlie has given most of the information about me. I want to add to MICES because it's upcoming, it's in June. So if you happen to be in Europe, maybe you can come to Berlin for Buzzwords and MICES. And this year at MICES, we will have a pre-conference training, so to say, and that will be search relevance for product managers, so search relevance in the e-commerce space. And it's organized by Open Source Connections. Eric will be the instructor together with TwoDoc. And these are our sponsors as well as at MICES. MICES is very community-driven, so please feel welcome. Okay, so today I'm going to talk about query relaxation. Maybe not the best topic right after lunch, relaxation, comfortable seats. But I can promise it's a hard topic, and I want to start this topic from the UX perspective. So zero results makes us feel uncomfortable. So also makes our users uncomfortable. So basically, if a user sees a zero result page just like that, it's very likely the user will go away. Yeah, so, and I think it's also to some degree a conversational problem. Yeah, you should at least tell the user a way out of this. And there are a number of strategies around to avoid the situation or to help the user out of this situation. So first of all, of course, we want to avoid zero results, and we apply a number of strategies to do that. And so one of these strategies is query expansion. We'll have a talk about query expansion later today. So we apply synonyms or hypernyms that somehow broaden the query. A different strategy is spelling correction. So our did you mean, you've searched for. So the user, when the user sees that, the user might realize, okay, I've mistyped the query, and this is the way out of that. Another strategy here is also search in low quality fields. So in the context of e-commerce, by the way, most of my examples today will be, or almost all of them will be e-commerce related because that's the domain I work in. So searching low quality fields could mean my first pass search would be in the title field and in the attributes. But then I might have some content and low quality descriptions, maybe optimized for SEO, so a different type of findability stuffed with keywords. This is something that can really harm my precision, and I might search in that field as well. Yeah, so I haven't found it something in a precise way. Now I'm going there. Then I might also have a strategy to overcome zero results that would be loosening my Boolean constraints. So that means turn from and to or maybe. Yeah, so conjunction versus disjunction. Or those of you who are familiar with Solar and Edis-Max, there's also this minimum should match parameter that says, okay, how many of the optional Boolean clauses are required to match. Yeah, so that could be 50% of them are optional, 50% must match. So I can do a first precise pass, search pass, and then a second pass I say, okay, only 50% have to match. So if that fails, we can also say, okay, maybe it's not hyponyms, but hypernyms we want to do. So if you would have a query like boots, and then we would have specific boots, but if we can find or can't find boots or more specific boots, we go the other way around. So we go into the direction of shoes. Yeah? So normally if someone searches for boots, we won't expand it this way, but as we go down those strategies, this might come in handy as well. And then we are going more and more away from the original intent of the query, and we might show related queries. Yes, someone searching for beard balm, we show results for trimmer maybe. So it's still related to this problem of finding beard balm maybe, or grooming. And then way out of this, there's more general strategies, more general recommendations. So we show maybe items related to the shopping history of that user, or generally popular items. So the overall idea would be, first of all, try to help the user somehow related or very much related to the query intent, and then, or the actual information need, but then go to the more general intent. If you look at those strategies, how explainable are they to the user? And some of them don't need an explanation, like synonyms. We just apply them. Spelling correction, did you mean? That's the pattern, so we can explain what we did. But then search and low quality fields, well, we don't want to tell. At least not in e-commerce. Maybe if it's more research-driven, that might be a valid thing. And Boolean constraints, loosening Boolean constraints, nothing we would do, or we could explain in e-commerce, but maybe that would work if that's a platform like pattern search or an explicit query building. So all these strategies have different quality when it comes to, can we explain it? And now let's enter query relaxation. So I think you might be familiar with Google's approach to this. So query relaxation, basically what it does is it takes a query and then says, okay, we don't find a match for the conjunction of the queries. So if we apply a Boolean and we want to remove one term, and then we tell the user which term we removed. So this strike-through pattern, I think that's very common. And finally, Google applies a very nice strategy here to get into a conversation with the user, because then Google also gives us a way to say, no, it must include this term that you have just removed. Yeah, so I think that's a very nice pattern, UX pattern for query relaxation. I have to say I really had to find a query, or struggled finding a query for Google to show this pattern. So of course, query relaxation is one amongst many patterns, and but I think it's really useful when you want to explain what you did, or it's nicely explainable. The big question then is, which query term should be removed? And this is really difficult and a really hard problem. And I want to go with you through a couple of examples and look at the intuition that we have, which term could be removed. So let's look at a query like iPhone 9. And so if we say, okay, will you remove the 9 and just search for iPhone, maybe that looks good. But if we remove the iPhone and keep the 9, we would search for 9. Yeah, so 9 would produce a lot of silly matches, so that doesn't make sense. So it looks like, okay, let's remove numbers, but maybe not always. So if the query looks a bit longer, like iPhone 9 Plus, we might just remove the plus, because the iPhone 9, that's the same generation of iPhones, like the iPhone Plus. We might say, okay, the user might be more interested in the plus than in the generation. So I think it's the size of the iPhone. So we might remove the 9. But removing the iPhone totally, maybe that's a problem. But you might find users who do that. Yeah, so they try out all the variants, and then they search for 9 Plus maybe. Another candidate, apart from numbers, might be colors. So colors is a candidate to be removed from a query. So in this example, we have black boots as the input or as the non-relaxed query. So we don't have any match for black boots. So we show boots as a query. So we offer this. And maybe just being left with black doesn't look so nice, but maybe it works. So have a look at this query. So if the query is purple boots, of course you can do the same thing, remove the color. But then I would think purple is a very strong color. Yeah? So if someone searches for purple boots, maybe purple is more interesting for this person than boots. Yeah? So how do we solve this? And I think the problem here really is we can hardly come up with a very strict intuition. And if you look at this example, USB charger, 12 volt, all of them are important. Yeah? So assuming that our data is okay, we cannot just remove any term here, because then the user would not get what the user wants. So it seems like it's difficult. Yeah? So building a good intuition for that is a problem. If you come back to our strategies, I think if you look at the top of those queries initially, there are strategies that allow us to stick as much as possible to the original information need. And on the other hand, there are suggestions, query suggestions, that just are remotely related to the user intent. Yeah? So our aim cannot really be to repair the query like in the top listed strategies, but then we have a strategy here, and query relaxation is one of them, that is more of a recommendation maybe. And it took me 4 months to figure this out. So I was struggling to find this way to exactly define how I can repair the query using query relaxation. But really, it's not about that. It's really about finding something that's related to the user intent. If you look back in history a bit and try to find how query relaxation was dealt with over time, we see initially it was something that came up in Boolean retrieval, working with databases. So we manipulate the query constraints, maybe using a query builder, and only the more recent approaches look into query relaxation as it is, and as something that is only somehow related to the user interest. Yeah, so I think this has also changed a bit. So this question still is, how can we find the best term to be removed from the query so that the result still contains items that are interesting to the user? And then how can we compare and test and optimize those solutions? Let's have a look at online testing. So how would we test our query relaxation? And here I would say it's more or less click-through or hit rate. So hit rate is more popular in recommendations. So the idea is how many of my recommendations did get a click. So every time I show 5, did I get 1 click at least, 1 or more clicks? So that counts as a success, yeah? As opposed to how many of these documents were clicked, or as opposed to the ranking of those documents. We're just interested that we get a click, and I think this is what we should track for query relaxation. And then, as I said, it's more about recommending things. The other metrics or further metrics relate more to the dwelling time of the user on our site. So we look at exit rates or time spent on site that we can improve using query relaxation. So it's, I think, in this respect, more similar to recommendations and maybe exploratory search. So now let's look at how can we find a good algorithm, and how can we create such a solution, and how can we test it. And to do this, I think we need a data set, and we need a data set derived from tracking where we observe those pairs of queries. Yeah, so a long query, many terms that doesn't match, and the short query that is reduced by 1 term and that has matches. Yeah? So we need a database of those pairs. So in the experiments I did, I used 2 of those query sets. And the first query set is just query frequencies. Yeah? So I'm just saying, OK, I don't want to look stupid, and I don't want to leave the user there with just the 9. Yeah? So I'm looking at, can I find valid queries? Yeah? So that's, and so I go to my tracking and look at the query frequencies and look at the long queries and the short queries, trying to find pairs. And then the long queries should have 0 results, and the short queries should have results or must have results. And then, of course, it doesn't mean that the user would necessarily correct the long query or accept the shorter query for the long query. So obviously, we would like to go to user sessions and see whether we can find the original and the rewritten query, the relaxed query, in the same session. So that's my second query set here, looking at those co-occurrences in the session. And then basically, we just said, OK, did they co-occur? And then we might have more than one candidate for the rewriting. Yeah? So maybe the query has 3 terms, and we find 2 terms versus 2 terms like ABC is the input query, and we find AB and BC in our tracking. And then there might be another approach that says, OK, I want to predict the query that is the most likely, that has the most observations. Yeah? So if AB is more frequent in my data, I want to predict AB as opposed to BC, which is less frequent. So we can apply this better, worse for both approaches, for both data sources, and so have a variety of tests we can run and optimizations. So I want to start with a few approaches and algorithms that I tested. And I want to start with the baseline. So just remove a random term from the query. And so that's what I did. And I used the 2 query sets. I should use the pointer. So I used the 2 query sets. So co-oc is the one that has the co-occurrences within a session. So the original and the relaxed query co-occur in a session. And frequencies just goes to the query frequencies. So the 2 queries might not necessarily have occurred in the same session. And but we make sure, OK, we produce an acceptable query, so to say. And then the top split is about, so that's the best prediction we get, or the best observation we have. So we accept as a match only the case when we predicted the more frequent observation as opposed to the less frequent observations. And then the metrics we have are precision, recall, and then F1. And in this case, precision and recall are the same. So either we found it or didn't find it, and it implies the same score for precision recall. And as you can see, of course, the right-hand side is a bit better because we accept more solutions, more hits here, and the left-hand side is worse. And overall, the co-occurrence within a session data set is trickier to match, yeah, because we accept more queries in the frequency data set. OK, so that's our baseline. It's more or less below 0.5, or our metrics are below 0.5, apart from this one, where we just accept any query that we have observed before. So now let's try to create an algorithm to be more clever than what we see here. So the first idea I had was, OK, the 9 looks short, digits look short. Just remove the shortest term in the query. Yeah, so remove short terms. And I think Zipf's law tells us short queries are ambiguous and not very meaningful, or short tokens. The longer the word, the more specific it is. So maybe we can remove that. And we get a bit of a gain in this data set that looks at co-occurrences within a session. So the next thing I tried was, okay, then let's look at numbers. Yeah, let's try to remove terms that have a digit. And if you have more than this, we remove the shortest of them. Yeah, so that gives us a gain here. So that looks already, yeah, that's the most important gain. There should be another one here. No, it isn't. Okay. But then we have less recall, of course, yeah, because not all queries have a digit. Yeah, so they might have a shortest term, but not a digit. Yeah, so we don't have a solution using this algorithm. And I think many of those handcrafted algorithms that use at word structures, word shapes, have this problem that their coverage is low. And but I thought, well, this 0.52 in precision, that doesn't look too bad. Maybe I can combine the two. And so I said, okay, I dropped the shortest non-alphabetical term, so the shortest digit. And if I don't have a digit in the query, I fall back to removing just the shortest term. And this looks a bit better. So still, our precision is not very high in the co-occurrence data set, and it doesn't always help. Okay. So after that, I looked into term frequencies in the index. Yeah, so I would say, okay, maybe I can use that information. And I run two experiments. So one experiment is I drop the most frequent term, the term that's most frequent in the index, or the least frequent term. And this looks really nice. So the least frequent term already gives me pretty high scores in my metrics. And this is not just about zero, or terms that have zero occurrences in my index, but it's also about these terms are so specific. So users probably have modified their query in a way, or would modify their query in a way that they remove the specific term and go more general. So I think that that makes a lot of sense. So I kept playing, and another approach, obviously, is look at information contained in those terms. And how would I do this? I would look at entropy. So how is the term distributed over navigational categories? Yeah, so if the term is only contained within one navigational category, it has a very low entropy as opposed to it's spread across many categories. So that sounded reasonable to me, but it was a complete failure. So neither using the highest entropy nor using the lowest entropy did make any sense. So it looks like it's either unrelated to this problem or there's a sweet spot or anywhere in the middle. So it doesn't work using entropy. But still I thought, well, information, maybe semantics can help here. And so then I hit on a blog post by Daniel Tönkelang and on query relaxation. And he mentions a strategy using word embeddings. So I don't know how many people are familiar with word embeddings. I get a huge proportion in this room. But just to repeat the approach, so what we want to do is we want to represent a word using a vector, and semantically similar words should have a similar vector using cosine distance or cosine similarity. And the way it works is, here in this case, I'm using a context, yeah, like Paper Jeans London Slim Cut. And I remove a term here and try to predict it there. So I create vectors into a kind of a network. And I optimize those vector representations of the words that minimize my error in predicting the term. Yeah, so I get vector representations. So one such vector might have a size of 100 or typically 300 dimensions. And then I can say, OK, those two words are semantically similar. And I can use those vectors and try to represent my queries. And the idea is create such a vector for the original query and a vector for the rewritten query, and then see how similar are they. Yeah, and I try out all the query terms, remove the query term, and try to find out the most similar combination of two queries. So basically, that's what I've done here. So I used word vectors of 300 dimensions, and then tried to find the most semantically most similar queries based on cosine similarity. And this gave me quite a push here. So it is mostly the most successful, or in most cases, the most successful solution, apart from this case. So the term frequency is already very good, but then keeping the most similar query using word2vec already, again, gave me a little push here. Okay, so once I had hit on this idea of using vectors to represent similarity, I thought, well, there are different approaches to create such a similarity and map it to a vector space. And I'm always a bit suspicious of just using the sum of those word vectors. And there's an approach that uses the entire query as a word, so to say. So we, in the word2vec sense, and that goes back to an article by Grubowicz et al. And the idea is I can represent every user action as a word. Yeah, so as a vector and as a word similar to word2vec. And this approach somehow seems popular in Berlin, so a lot of meetups are saying, okay, we use this approach. And so I thought, well, I might be able to use this as well. So my idea is, by the way, I'm using Gensim to produce those embeddings. And so the idea is, this looks very similar to word2vec, but now our words are queries. Yeah? So smartphone 64G, the queries are the words now, so to say. And instead of using a fixed window of text, I'm using a session. So that means these queries have co-occurred in a session, and so I can train an embedding for the entire query now. So, and then again, I would compare the query vector for the original query and the query vector for the relaxed query. And that didn't give me much of a push or of a yield, except for the co-occurrence data set. And I think this is very explainable because basically they use the same approach. It's about session data. Yeah? So the embeddings were trained on session data, and the test was done on session data. On the other hand, we get very low recall. Yeah? So because we don't have that many query vectors available, because we haven't seen all the queries yet. Yeah? So that's a problem. Okay, so I tried, and the next idea I had is combine the vector approach with a multi-layer neural network. So how does this look like? And then use the network to predict which query term to drop. So basically, or overall, it looks like that. So that's our network. We have two hidden layers. I have an input layer, an output layer. And I assume that my query has a maximum length of 8 query terms. And so each of those inputs represents one query term. I'm using an example query, which has just 3 query terms. So everything here gets 0 unknown vector terms. And then I use as an input my 300 dimensions from the word2vec. So basically, this represents the vector for Nike, this the vector for boots, and this is the vector for 11. And I run it through this, and then here I have an encoding. Basically, if it's a 1, that's the position where I should drop the query term. So this says, OK, drop the boots, and maybe Nike doesn't make boots. And then all the others are 0. It's a kind of a soft max output layer. So where does it get me? So again, this looks better than anything we had so far, apart from one occasion or one test. So I think this is a very mighty approach. And in the end, I thought, well, now that I have a neural network, I can model in further features and go back to those initial features that I was using and just add them as an additional dimension in those vectors. So I was looking at word length and add them to the word-to-vec representation, the embedding, the number of digits, and also it seemed to make sense to look at whether there's an E in the last two positions. Yeah, so somehow that makes a distinction. So how does our network look like then? So basically you can imagine the 300 dimensions of this word embedding vector up here, and then I add a dimension for the word length, a dimension for the number of digits in this word, and a dimension whether there's an E in the last two positions. So Nike has this. So this has word length 5. This has word length 2 digits, but no E in the end or in penultimate position. OK, so yeah, so that's the best one. So this is as far as it gets. So we are very high when it comes to the frequency data set. So that's around 0.9 for recall and precision, and already high-ish when it comes to the co-occurrences. And the nice property of this approach is that we can model in, factor in further features. Yeah, so I have stopped at this point and not tried to find further features because we know, okay, if you want to improve further, we can try that, and we have a model. Just add a further dimension here where we can add another dimension for a feature. I've tried, I lied. I've tried two more things, adding frequency information, but it didn't work out. So basically, the features there, using those word shape features, is plus the multi-layer neural network based on word-to-vec helps a lot. So altogether, putting it all together, I think what it shows is query relaxation is best understood as a query recommendation, yeah, because it's very hard to see a query relaxation that it will be able to fix a query, or to fix the intent or the information need. It's the information need that the user has could still be represented in the query, but still the major goal for us is to keep the user in the conversation, keep the user on our side. The best approach that I have found is the one that uses the multi-layer neural network combined with the word-to-vec as the input, plus those word shape features. And as I said, we can try to model in further features there, maybe combine it with the query embeddings or whatever. We could also model in seller interests. Yeah, so we could say, OK, we want to promote queries that yield a lot of profit, maybe. Yeah, so we can model. So the model would enable that. So yeah, that's it on query relaxation. I haven't spoken about how would we decide when to use query relaxation. Yeah, so that was my prerequisite. Once we have decided we want to use query relaxation, I think that would be the approach that I would choose, and it has made it into production with 2 clients so far. Yeah, thank you.
Thank you very much, Rene. Do we have any questions for Rene?
What was the motivation for the feature that used E at the end of the word?
I think this is NLP toolbox. So sometimes NLP looks like voodoo. We count something is we take the 2 letters of the previous word, and is the next letter the next word capitalized, things like that. So I would say, well, that's based on experience, and E makes sense. In this specific case, I was looking at it was based on German. It helped in English as well. I was looking at plural endings, so that would involve an E in that position. I tried to rephrase it.
We need the mic for the recording, so I'll come to you.
Thank you. When looking at query relaxation on our end, one of the things that we thought might be valuable is to look at the part of speech of words in the query, thinking that
Yeah.
you're on an e-commerce side, objects are probably the most
Yeah.
important.
Yeah.
Did you do anything with that?
Well, I agree that I think the product type is the thing that maintains the original information need the most. Yeah. But then I thought, first of all, I find it often hard to predict the required product type. And then I thought, especially if you look at actual user sessions, users are prepared to give up the product type. Yeah? So I thought I cannot solve it exactly, so I go to the statistical method, and I think it might be encoded in the neural network in some way. But yeah, I mean, a completely different approach would really be to use a taxonomy and look at or an ontology and look at the graph within the ontology and try to find relatedness within that ontology to predict which query term is somehow redundant, maybe. But I haven't explored it yet, especially as I didn't have an ontology here.
Okay, do we have any further questions?
I may have missed this, but you could use a topic model there at all?
Yeah, I think that could make sense. So I think it would it produces topics and probabilities. So I think we could try to model this, though I'm a bit skeptical with query terms that we haven't seen yet. So in the neural network approach, it's just a zero vector, but still the other features could kick in. So I would think if we looked at this, we would probably use it in combination with another approach to account for those cases.
Can you talk about more, how did you use the neural network, like about the training or?
Okay, so so I did training and test set, and the vectors, also the word embeddings, were only trained on the training set terms. And it was like 75,000 for training and 25,000 for testing. And the layout of the network, it's 2 layers. So the first layer is 512, size 512, and the second one 256, with a dropout and flattening in between, and cross-category entropy as the loss, so to say, and LDM optimizer. So pretty standard, I think.
Google has recently published. So I've heard that Google has recently published an algorithm known as BERT, which is the next version of word2vec. It captures the semantic relationships in a much better way than word2vec. So
Yeah.
you might probably look into that to
Yeah.
improve it.
So basically, I think also even within the realm of word2vec, so I use continuous back of words instead of skip n-grams. So there's stuff you can play with. But if you look at those metrics already, I would think it doesn't get much higher, maybe a bit. And I think I would more look into the additional features I can integrate. But I agree, semantic relation, this somehow relates to topic modeling or using the part of speech and so on. That could be useful. So yeah, it's not the end of the story. Yeah.
Can you clarify what the metrics are here? So like could you clarify what the metrics are here? So what exactly is precision measuring? Is that the precision of the new query? Or is
No,
that
it means the number of precision of the new query. So is the new query so let's look at the data set. In the frequency data set, it means is the new query a query that we have seen before, so to say. Yeah? And there it means, for the co-oc data set, it means have we seen this pair of the original and rewritten query before? Yeah, so and if we miss it, it's already a drop in the recall. So this is why it goes in the it's one-to-one, so to say, in the first metrics. But then we might have algorithms that are not capable of making predictions in certain situations. Like I don't have a query vector in this case. So this is why I say I can't make any prediction, so to say. Or I know there is one and I cannot bring it back. Yeah.
Okay, so it's not the precision of the search results. It's the
No.
It's whether or
yeah,
not the query.
exactly.
Okay.
Yeah, in that sense. Yeah. Yeah, I was thinking about using accuracy versus precision, but I think precision is the better term or the better approach here. Yeah, and again, I think we are not really looking at search results, but really about the prediction. Yeah.
What about the performance of the analysis? Is this something you can do in real time, or is it rather a background processing thing?
It's real time. So we use TensorFlow for this. So, and it was performant enough. So Java bindings to TensorFlow, and it works okay.
Do you have any evidence or any intuition as to whether or not the research findings from this work would be transferable to other domains outside of e-commerce?
Yeah. Consultant answer, it depends on the domain maybe. But yeah, I would think so because, I mean, especially for the word-to-vec approach, I would think so. Maybe shortest query term is a bit different. Like in e-commerce, digits are some kind of, model number, or I don't know. So they have a specific meaning in e-commerce. But overall, I think it could be met. But it might be interesting to discuss other domains as well. Yeah.
Okay.
I mean, one thing is if you go to the co-occurrence approach, I mean, this is a lot sparser than just query frequencies. And if you're in a domain where you don't have enough data, if you don't have enough sessions or not enough co-occurrences in a session, that might be a problem. So e-commerce and user-facing often has. Yeah.
Okay, I think we'll leave it there. Going to ask you to please give Rene a round of applause. Thank you very much. And thank you also for some excellent questions.